My name is Grant Murray. I am a software engineer at OpenStore, specifically working in data infrastructure. So to run through what we're going to talk about today, first of all, I'm going to give you some context on OpenStore, who we are. We're going to talk through the context that matters as it relates to our business. And then we'll go through some problem definitions and disclaimers, align on some common terms, and then give you kind of an intro to the framework of the system that we're going to talk about. And then we're going to go through two different implementations of the solutions that we kind of came up with. The first being a PySpark solution, the second being a Snowpark solution. Run through the comparisons, talk about the technology at the infrastructure layer that kind of supports some of it, then give you some insight into what we're doing, looking forward in the next couple of quarters, and just talk about some resources that might be helpful as other customers are looking at a similar kind of migration. So in terms of about us, OpenStore is an e-commerce aggregator, and we were founded in early 2021, and we currently have about 115, give or take, employees based out of Miami here in Wynwood. And we operate a growing portfolio of dozens of e-commerce brands. To give you some context on kind of what that means from a data side, our public-facing SLA to Shopify merchants is that we will turn around and offer to them in a day and give them cash within 2 weeks. And we say move on in 3 months, but really we do it a lot faster than that, so long as everything goes well. And so the speed around this definitely is one of the things that makes working in data at OpenStore kind of interesting, stressful, but definitely engaging. Background context is that OpenStore has used Snowflake since our inception in February of 2021. And so I joined the company in mid-2021. And so this decision was made before I even got here, but it was very great from my perspective because I actually used Snowflake in the 5 or 6 years prior at my old job. We ingest data for a very large volume of Shopify merchants every single day from dozens of external data sources. And the SLAs on these data feeds vary from a full day to several hours or minutes behind the source systems. And we use this data intraday to both price prospective merchants that are coming through our ingestion funnel, which is just our website, open.store, and to operate a growing portfolio of e-commerce brands. Now, when we ingest this data directly into a cloud warehouse, because we're doing it from many sources and for many different merchants, this really results in this sharded data pattern that we're going to talk about today, where like data is spread across hundreds of databases, tens of thousands of schemas, and hundreds of thousands of tables, if not millions. And the real kind of hook, the complicating factor in this is that an external API can return different schema definitions across merchants within the same data source, like Shopify. So it basically means that all of the data structures that you're ingesting are not necessarily compatible with each other. And so to kind of put that a little bit more simply, if you ingest Shopify order data for 10,000 Shopify merchants, you might end up with 10,000 distinct versions of the Shopify order table. And the challenge that we were faced with that we're going to talk about today is how do you unify those 10,000 tables into a single table to operate on it as a single asset? And how do you do that efficiently, effectively, and reliably? So upfront disclaimers, I think we were definitely some early adopters of Snowpark, but that's likely a result of us being technologists and also not being thrilled with our PySpark implementation at the time. Today, we're going to talk about key features of Snowflake, both Snowpark and other, that are really key to the systems that we're going to talk about. But there's obviously lots of bespoke code and technology that also feeds this that is kind of left out. But today, we're focusing on the components that are really available to all Snowflake customers. The diagrams that are shown have been simplified as best that I could for the topic and the audience. And then, the last thing is just that we're literally 2 years old to the month almost. And so please keep that in mind as we walk through this because all of our technology is definitely a work in progress and subject to much more evolution as time goes on. So in terms of common terms, this is really, probably most of the audience is quite familiar with this, but this is really kind of the object model that we need to keep in mind today, where you have databases, and within a database, you have schemas, and then within schemas, you can have many types of lower level objects. But the ones that we're going to focus on today are really tables and streams. And so as it relates to kind of going back to the how do we consolidate 10,000 order tables into a single order table example, these are the three considerations that really matter the most, which is change data tracking. So how are we going to actually understand what has changed in the data since we last read it? What are we going to use for the Snowflake connector? So obviously we've got to communicate with Snowflake. We have to manage a lot of artifacts. What connector are we actually going to use? And the options there can be anything from the native Snowflake connector to a PySpark connector to Snowpark, a lot of different options, but we have to communicate with Snowflake somehow. So how are we going to do that? And then the compute itself. Obviously, a lot of data has to get processed here. And so how are we actually going to manage that compute and what is it going to run on? For the first solution that we're going to go through, for change data tracking, we use Snowflake Streams, which is probably the core change data tracking mechanism available in Snowflake. We were already running on PySpark, and so we use the native PySpark connector for our communication with Snowflake. And for the compute, we were obviously running on PySpark. And so what this looks like at a high level is essentially this diagram. Now, we're going to walk through this in more detail in the coming slides, but just at a very, very high level, if you just work left to right on this page, Open.Store is our website. And so a merchant will land on our website, and within 10 minutes, they will have authenticated us to spin up connectors for any number of data sources. These are just 5 examples. Those connectors feed data directly into Snowflake into a series of ingestion databases. And then what we were doing is we were pulling that data out of Snowflake and basically doing the process of standardization, schema merging, a lot of kind of compute intensive work in Spark. And then we were pushing that back into Snowflake into what we would refer to as a consolidated data set that was then picked up and processed further for, basically just taking that, honing it in, and making it really stable set of data structures to be operated on for internal functions, ops, marketing, pricing, etc. Now, to make this more tangible and more concrete, we're going to walk through this end to end with an illustrative 5 merchants. So 5 merchants landed on our website. That's the left-hand side. The connectors that we would spin up for them would basically be for these 5 example data sources, 5 merchants. That means we'd have 25 connectors total. By the time we actually get inside of Snowflake for this, we have an ingestion database per source, an ingestion schema per connector. And if we, as an example, to make the number simple, had like 10 ingestion tables per schema, that means that just for these 5 merchants, we have 5 databases, 25 schemas, and 250 tables. We were then pulling that out of Snowflake to do anonymization and masking, topical standardization, but most compute intensive wise was to do the actual schema merging, and then pushing that back in to where instead of having 25 schemas, we actually had 1 schema per source, so 5 schemas total, and 1 database with 50 tables instead of 250 tables. To kind of bring the parts of this that matter into something that's a little bit more digestible, I'm aware that font is hard to see on here. It's quite hard to see. Essentially, at step 3, we had, as I said, 250 tables, and at step 5, we would bring that into 50 tables. And the important part is that 50 tables stays constant as the number of ingestion tables scales. So for these 5 connectors, we could have 20,000 tables, and we would still be reducing them into 50 tables, with the really compute intensive part of that work being run on PySpark. And to make this even more concrete, numbers-wise, at the time of launch, and again, the font's tough to see, but I think at the time of launch, this supported about 5 external data sources and about 20,000 connectors, which resulted in about 80,000 ingestion tables that we were bringing into about 50 consolidated tables. And at the time of launch, this worked pretty well, but I think that none of us were thrilled with it when it went out the door, and it kind of quickly started to cause us some issues. So in terms of what those issues, challenges were, I think there were probably more than would fit on this slide, but to call out a big three, the synchronous read operations were a pretty big problem and not something that we at least easily found a way to get around with the PySpark connector. And so because we were maintaining the initial structure of each of these source ingestion tables as we were reading it out, that meant that every single one of them had to have an individual select statement executed against it. And temporally, for a lot of reasons, that obviously just doesn't scale very well. The stream management was also painful. If you're familiar with streams, you'll know you start with a table and then you create a stream on that table. And then when you read from that stream, it empties. So in order to maintain kind of an exhaustive system, you also have to have another table to empty that stream into to make sure that you're not losing any data with that exchange. And that really meant that we had to triple the total number of artifacts to manage, which if you don't have a lot of artifacts, that might not be a big problem. But for us, with hundreds of thousands of them, that definitely made things a lot more painful. And then the big one is just kind of the infrastructure burden. Like the MapReduce technology is not, if you have a core proficiency in it, then it's something that I'm sure people have ironed out exactly how they like to deploy it, how they like to manage it. But for a small team, a growing company like of our size, it definitely was more infrastructure burden than we wanted to take on just to solve kind of this component of our data stack. And so the second iteration of this really kind of came about when I found out about Snowpark for Python, and I just instantly texted our contact over at Snowflake, and I just said, hey, can we get early access to this? Because I'm ready to try it tomorrow. And obviously, yes, that went great. And so the next solution that we really went with was, instead of using Snowflake streams for change data tracking, we used Snowflake changes, which is pretty much like a stream. It just means that we're accountable for the offsets to track the changes between, not Snowflake. For the connector, we switched from the PySpark connector to just using the straight native Snowflake connector for Python, not even the Snowpark connector. For our purposes, we were just doing very simple reads. We needed to run them asynchronously, and we're happy to manage all the raw SQL beneath that. And so we just use the straight Snowflake connector. And then for compute, obviously, this is all running on Snowpark. So in terms of what that system actually looks like, very similar to what you saw before, except we just don't have that piece at the bottom where we're actually pulling the data out. And there are a couple key differences. The first is that instead of using streams, we were just reading changes within offsets that are tracked separately from the diagram that you're seeing here. Another big one is that we weren't actually maintaining the table structure. So we're taking advantage of the ability that we can just turn data to blobs inside of Snowflake. And then that took a lot of the complexity that we were dealing with while we were reading it and pushed it further downstream. And then we were doing this asynchronously using the Python connector, which obviously benefited the speed a lot. And then on the actual compute heavy piece, PySpark, totally out of the picture, all of this running straight in Snowflake. We obviously have lots of experience with Snowflake already, understand how to scale it, understand how to manage it, and there wasn't really a learning curve for us there. And so it was very easy for us to just pretty much lift and shift this and just start running it on Snowflake off the bat. And again, to kind of zoom out a little bit, aware probably that text is not legible, but for size-wise, at least when I made this slide the first time, this was supporting about 25 external data sources, over 100,000 live connectors, which was resulting in over 500,000 live ingestion tables. And then we were consolidating that down into 250 unpacked tables, not consolidated tables, because we're turning them from blobs to tables as we unpack them from kind of that ingestion changes semi-structured database in the middle. And so it's something like, I think now at this point, it's over 15 or 20 times what the solution one was when we deprecated it. And it's not even really sweating at all. And to really kind of lay out those unlocks, there are four, and then the first two kind of compound on each other. So, and the top two, the two that compound on each other, don't have too much to do with Snowpark in particular. They just really overcame some challenges that we had without this ability. And so JSONifying tables to blobs, that was huge because it meant that we didn't have to actually keep the table structure in mind as we were reading it. And then that basically decoupled that really complex application logic from just getting all of the data consolidated at once. And then using the Snowflake connector over the PySpark connector let us do that asynchronously. And so instead of having to execute, if we want to talk about 10,000 order tables, instead of having to execute 10,000 statements to read all those tables, we could execute 10 statements and just read 100 tables at a time by turning them all into blobs and stacking them on top of each other. And then changes versus creating streams. This was another pretty big one. Again, streams could be perfect for your use case, depending on what your architecture looks like. For us, they were definitely challenging. And so by just keeping track of the offsets ourselves, it let us take our total number of artifacts to manage from about 1.5 million tables to 500,000. And then this also enabled us to really elegantly repipeline historical data if we wanted, without having to go through all the trouble of tearing down streams, tearing down the tables that we were using to dump those streams into. And instead, just all of the existing artifacts could stay as they were, and we could just replay data through them based on offsets that we provided. And then Snowpark for Python versus PySpark EMR. I mean, I think we're a pretty good success story here because it has just it just worked. And I think I've used Java on Snowflake a pretty significant amount before and had good results with it. So I'm not surprised that it did, but it achieved 100% parity of what we were doing with the prior PySpark workloads. It removed all of the infrastructure overhead because we're already well set up to manage Snowflake, already do it kind of in our sleep. And it improved the ease of scaling and ongoing reliability immensely. And to put that in numbers, we pretty much had a 90% reduction in runtime, and our throughput per job increased by 25%. So we were taking 1/10 the time and processing 1/4 more data. And then I had to put something on here related to upkeep, and 80% was kind of just a gimme number, but we took one person's job on a team that was definitely taking a majority of their time and just completely got it back. And then from a raw dollar standpoint, it also is actually saving us money to do this as well, even once you take out that engineering upkeep back. And so it was just quite a huge win. And as I said, I think we did this work probably about 6 months ago, and it's still running today and not even sweating. And so that's been great because we've been able to move forward with other problems that we've had, and this has continued to do its job like a champion. And I can't just talk about the Snowflake piece without calling out some other things that we use quite heavily in here. We use Terraform to do all of our resource provisioning, which definitely makes all of this a lot more stable, a lot more portable, pretty vital to what we do. Kubernetes, we use very heavily. All of this stuff runs in Airflow on Kubernetes pods, and that level of horizontal scaling is really necessary to support these kinds of workloads for us. dbt had to be in here because we use it a lot in a lot of different ways. I think that net, I like dbt, but I think it can definitely be abused. But it used in the right way, it can definitely help you avoid boilerplate SQL and keep a lot of this more where it needs to be. And then Datadog for instrumentation is absolutely necessary. You can't manage these kinds of workloads without actually understanding what's going wrong, how much data is moving, etc. Looking forward, we really just want to revise the low-level storage architecture to better support multi-tenant consumption. We want to integrate our schema definitions and contracts into something like Apache Avro for data connectors. We already have a data connectors platform, and that just needs to be kind of a first-party citizen there. And then internal tooling needs to evolve as well, and that's mostly things around dbt and Airflow. Much of this is done through metadata that's available through Snowflake, and investing in that really helped us out. Account usage databases and the object tagging model was vital to kind of managing this level of artifacts efficiently. And then, it took a ton of work. These are 2 solutions, but it was really probably 3 or 4 that we went through. And so perseverance, trying again, and implementing better technology was kind of the win here.